Good morning, everyone. I'm Jiayi.
I'm Anapa.
I'm Jessica.
I'm
I'm
Shiva.
Benjamin.
I'm Joseph.
I'm Kiana.
Okay,
I'm Sharmishta.
Today I'm excited to introduce our VIP project, Energy Predictor. Let's dive into the background for this transformative tool. To start, let's discuss the role of surrogate model in urban regeneration. Traditional energy simulation help architects and planners assess the environmental impact of different design choices. By comparing the urban footprint, energy usage, and other sustainability metrics, they can make informed decisions about building design and operation. Moreover, energy simulation supports the integration of renewable energy solutions, helping reduce peak energy demand and meet sustainable standards. The challenge, however, is that conventional simulation methods, while accurate, are time-consuming. This is where machine learning-based surrogate model came in. This model offers real-time feedback, allowing urban decision makers to act quickly and efficiently in designing more sustainable cities. And now we come to why to gamify energy modeling. Energy simulation is crucial in design, especially for meeting standards like LEED, but traditional methods often happen too late in the process, reducing their impact. A Harvard study found that a game-based approach to energy simulation leads to office design with 22 to 31% lower energy use intensity, with students preferring for its interactive and early-stage feedback. Gamifying the process allows designers to explore options and make efficient choices from the concept stage. And for current solution, now let's look at the limitation of current workflow. Traditional energy simulation flows a multi-step process. Data collection, building where we gather detail on building geometry, usage characteristic, and climate data. Simulation setup, selecting software, defining the scope, and inputting parameters. Running simulation, a step that is typical time intensive. Analyzing results, evaluating data accuracy, visualizing energy use pattern, and identify area for potential energy saving. Design iteration, a repetitive process to refine energy saving solution. While these workflows produce accurate results, they are not scalable for large, complex urban projects due to their computational demand. To overcome this barrier, we are shifting towards machine learning and data-based model. This model offers scalable real-time insight, making them far more adaptive and efficient.
So for our solution, this is what our simulation workflow looks like. Because we wanted to develop a statistical machine learning framework to evaluate the impact of 10 predictive variables on both heating and cooling load, we first got data for commercial buildings in particular from the Comstock dataset, and also we supplemented the dataset using the Open Studio simulation files by NREL. Once we had our data all set up, we first cleaned it and then also encoded it so that it could easily be put into our machine learning model. And once we had our data set ready, we then also cross-validated it and used feature engineering to select our model, which we were then used in our game. So here you can see, if you could go, yes. Here you can see what our data set looks like. And because of the characteristics of the data set, we were most likely going to use a tree-based model and not a linear regression or a random forest model, because tree-based models, because our data set is so complex, it would more likely be a better reflection of how it can predict the values. And here we end up choosing the gradient boost method. And here you can see that the R-squared values for both the training and testing dataset is very high for the gradient boost method. If you look closely, XGB does end up performing better here, but we'll see very soon why we ended up choosing the gradient boost method. So once we fine-tuned our gradient boost method for both heating and cooling load, we saw that the R-squared value increased from 0.919 to 0.945 on the training dataset and from 0.9 to 0.935 on, on the testing and then the training dataset. And we used Bayesian optimization and grid search to fine-tune our models, and this actually ended up giving us a better result than XGB.
Okay, and recently I just update our data set, and I add 3 new additional features, including world type, build year, and window type. And maybe Jai, go next page. I just find, and I run our model again on the new data set. I just find our model performance increased a lot. We perform better on the new data set. So let me explain on this table. So especially for some traditional parametric regression model, for example, multiply linear regression and the spot vector machine perform much better on this data set compared with the previous data set. And of course, on all of the other machine learning models. And we can see the red number represents how the value change compared with the previous data set. The red value means its performance increased. The green value means it decreased, and we can see almost all of this model have a much better performance, especially for extra tree, decision tree, and the decision tree. They have even R square equal to 1 on training data set. And I would say it's not kind of overfitting because it also have some good performance on test data set. But overall, I would say it's still gonna be a graded booster model is the best model. And if we have model like this, all of this model have such good quality. That's the reason why I considering to develop it into a conference or journal paper. I think the quality is good enough for publication. Yeah.
So here we have our tech stack for our game. So on the left, we have our backend tools, and on the right, we have our front-end tools. So starting from the left on the bottom, the backbone of our data is the Comstock dataset. So we use this dataset to set the default values for different building types, which gives users a baseline to work with. We also had to simplify parameters to make the interface a little bit better to interact with. So one example of this simplification was how we combined window and wall areas into a single metric. So it's window to wall ratio now. So instead of asking the user to input window and wall area separately, they just have to input one. And in order to connect our predictive model to the interface, we converted our GB model into SAB
Jessica,
files.
we're still on the tech stack. Sorry, I don't know if you're talking about the demo right now. I see the tech stack slide currently. Sorry.
Yeah, we're still on the tech slide. This is a kind of long slide. But yeah. So we converted the GB model into SAB files using scikit, and then we use this Python script to load the models into Flask to create a server that our front-end interface connects to. And this setup allows the user to be fed into the model, the user input to be fed into the model, and also allows the model to display an output on the front end. So on the right, we have our front end tools. So we use Blender to create the models, and then we use Three.js to import those Blender models into Three.js. And then Next.js was just used to combine both front end and back end. So it takes care of all the local storage and like retrieval logic. So here we conducted experiments to assess how effectively this tool supports the evaluation of different design choices for reducing energy load. So the goal of this game is to simulate early design, the early building design phase and to optimize the project according to specific role-based priorities. So in this experiment, all the players chose the same building type, which is office. And the players are free to change any parameters, and they have 5 attempts to basically meet their goals. And so on the left, let's say I'm an architect. So as an architect, I'm interested in the building shapes, height, window to wall ratio. So let's say I initially went with a kind of 60 window to wall ratio of 65%. So that's kind of high. And then if we run that, we get a kind of high heating load and also cooling load. And then we could also decrease it. And then we'll see that we'll get a smaller heating load and cooling load. And so this is important for occupant, the window to wall ratio is important for the occupant's comfort and productivity. So especially in an office setting. So this is kind of important. And on the right, we have ESG consultant. So with the ESG consultant, I'm basically focused on minimizing energy consumption. So here, I think initially we have a high window to wall ratio just to get a baseline. And then we change it to a rectangle. And then we decrease the window to wall ratio. And then we can see that the heating load and cooling load decrease significantly. So that's an example of how I would use this tool. So these are the experiments. So these are the results across 6 people playing the game. And we can kind of see trends for both architect and ESG consultants. So on the left, we have the architect simulation results, and we can kind of see that it starts with the kind of high heating load and cooling load, but then by the end, all 3 architects have a lower heating load. And on the right, we can also see the ESG consultant simulation. So here we can see a more dramatic difference between the starting heating load and cooling load and the final heating load and cooling load between all 3 people. So we can kind of see this downward trend because their main goal was to minimize energy consumption.
So we use Climate Studio to validate whether our model predictions are accurate. By comparing the results from Climate Studio with those from Comstock and surrogate model, we aim to verify the reliability of our predictions. Next page. And so the following outlines the process we use for validation with Climate Studio. And next page. So we conducted a total of 10 validations, and here we present part of our validation results. And the results showing a comparison of the input assumptions and the outputs for cooling load and heating load. Next page. And these are our results and findings. Firstly, the validation results differ from loads of the surrogate model. The surrogate model's cooling load values are close to those of Comstock. And secondly, both values from the surrogate model and Comstock significantly deviate from the results validated using Climate Studio. And lastly, the results from Climate Studio are questionable because in Atlanta, the cooling load is typically expected to exceed the heating load, but our results show the opposite. And we will take a closer look.
So in terms of our future directions, given all the progress that we've made, one thing that we are looking into is the creation of a website where you can click on a building footprint and it can return a predictive heating and cooling load. And so if we go to the next slide, we also see that there's various APIs we could use. So one of the APIs is the National Structure Inventory. And both of these APIs are essentially, we can use them to gather building data across the United States. And if we want to do something more specific to Georgia first before we expand, then this is also, you're also able to do it because the National Structure Inventory also allows you to choose various states and then download all the data for them. And the other one was the 131 million American buildings. So this data set essentially has data of various different buildings, but according to the documentation, there are some instances where some buildings do not have like the zip codes or the street addresses, but given everything else, like it gives us the general polygon, the shapes, and then various other information, this could definitely give us a good start or a good foundation for us to move ahead in terms of the data sets that we want to use. And it will probably get us about like 60% there. And that'll be like a good way of us having like a website where if we can make our own building footprints, we can then run our machine learning model, and it will give us the expected heating and cooling outputs. And the next direction we could take, if we go to the next slide, is also doing essentially more machine learning research. So we do have a model that works, and it's very documented, but there's also much more we could do, as in we can do more experimentation, more testing, and as you can see, we have done a decent amount of validation, and we realized that we could also make this machine learning model much more robust. And so one of the things we could try is trying to, experiment and get more complicated features we could look into, like let's see if we could add weather data into it, or, if we could add more things onto like the solar gain, or also understanding shape complexity, seeing how we can input that into our model, or how we can make our own data using the data that's already available, and then manipulating in such a way that it can give us a better result. And then finally, one of the main things that we're actually looking into in the next slide is finding a way to put our machine learning model into Rhino. So we could possibly use the scripting environment that Rhino has. And if we're able to put our machine learning model, and obviously as we have various iterations of it, we can find a way to keep updating that into Rhino. This could definitely have a huge impact for designers and architects, as when it comes to early stage development, it could give them a very good idea of, is the building I'm making going to be viable when it's actually converted into a physical object. But in essence, yeah, this concludes the presentation that we've had.